Hello students! Today we begin our transition towards a new chapter, single-order differential equations. And don't worry, we will keep the integration practice series alive with regular uploads. To kick this off, let's start by learning about the methods used for solving single-order differential equations. The first method is direct integration. This happens if we have a function in the form dy over dx equals f of x. In this, we multiply dx on both sides. Remember that for integration to take place, our dy and dx need to be in the numerator. We can integrate this then to get y equals capital F of x plus c, where capital F is the antiderivative of small f. The second method can be applied if an equation is separable, meaning it can be written as two functions. An example is if you are given dy over dx as g of x times h of y, then cross-multiplying gives dy over h of y equals g of x dx. This way we have all the y terms on one side and the x terms on the other and can be integrated next. What if the equation is homogeneous? Meaning an equation takes the form dy over dx equals f of x over y, or alternatively, dy over dx equals f of y over x, meaning that f is a function containing both variables. The most common method to solve this is using the substitution v equals y over x. Then the function just becomes f of v. Now we look for another way to write dy over dx, which is basically taking the derivative of y with respect to x. And from the relation we established earlier, we know that y equals v times x. So we use product rule for the derivative, which gives x times dv over dx plus v times 1. Now we can put our two dy over dx expressions equal and rearrange to have our two variables separate. Then take the reciprocal on both sides to get dv and dx in the top, and this can be integrated. An exact equation is one given by the form m of xy times dx plus n of xy times dy equals 0, and we have a function f such that the partial derivative of f with respect to x is m and with respect to y is n. Then the equation is said to be exact. And if we plug these into the top equation, this is just chain rule that just tells us that df is 0, meaning f is just a constant. Now to solve this first, we check if the equation is exact. If the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x, then the equation is exact. Now we need to find the function f. We can do this by integrating one of our terms. Let's say we integrate m. That will be with respect to x due to the dx here. This gives us f of xy plus c of y. The constant here depends only on y. If we integrated n, then the constant would only depend on x. Now we take the partial derivative of this with respect to y, and that is equal to n, as we stated earlier. We then solve for c, which is the constant of integration, and this is equal to f. Time for the last method, integrating factors. Given an equation in the form dy over dx plus p of x times y equals q of x. If this equation was exact, then we could just integrate both sides and find the answer, but most often that is not the case. An integrating factor is a function called mu of x, which we can multiply with both sides of the equation to make it exact. Now we focus on the left side. We identify that this is just product rule, or the derivative of mu x times y of x, which gives mu x times y prime x plus mu prime times y. Comparing tells us that mu prime is just equal to mu times p. We can divide mu on both sides in this equation. and integrate both sides. Evaluating the right side gives ln mu x. Then inverse natural log can be taken on both sides to give us the integrating factor as e power the integral of p of x. Now, to solve questions, we can identify the integration factor and write the terms as a product inside the differentiation sign as done here, then integrate both sides to get the answer. We will solve examples for all methods in upcoming videos, so no need to worry.